Hi, it's your guy Olumide. Today we will be solving another one of the most commonly asked tech interview question. Find all words on a board. It's a DSA problem that is commonly asked by top tech companies including Google, Amazon, Netflix, Microsoft, Meta, Apple, and other top tech companies. The problem statement states that given a 2D board of characters and an array of words, find all the words in the array that can be formed by tracing a path through adjacent cells in the board. Adjacent cells meaning that and when we say adjacent cells, they are those which horizontally or vertically neighbor each other. B here and R here are adjacent. B and Y are adjacent because they are horizontally or vertically. In the case of R, they vertically narrow each other. In the case of Y, they horizontally narrow each other. So by tracing a path through the adjacent cells in the board, so if we just want to return as much words as we can actually form, so by traversing adjacent cell in the board. So like we can see here now, in this same board, this is the board given to us here. It's a board, actually a 3x3 2D array, right? So you see that it has 3 rows and 3 columns, and then by traversing this BYTE, we can secure and form the word bytes, which is actually in the word, is in the word array. So and because of that, we have found one word, we have formed one word, so in the array of words. So by traversing through the board. Another one is that BYTES. BYTES, which is here, you see that we can form that as well over here. So also we can form rain. Look, RAIN is gonna form rain. Y train, TRAIN. So these are 4 words that we can form. We say that we cannot form traits because in the process of forming traits, we can form it, but it's not gonna be valid. Look, TRAIT. So it's gonna be coming back to the same letter that we use in that word. So don't forget that there's a condition here. We can't use the same cell more than once for a single word. So trying to extract traits in this particular array of board, or let me say in this particular board, is actually invalid. Why? Because though we can extract trait, but it will means we reaching the same cell 2 times for the same word. This problem requires that we search for all words in the array that actually in the words array, right? But we are gonna simplify this problem first of all to searching for just one word in the array, say bytes for instance. So we are not gonna consider solving for all words, but we are gonna be just touching one for now, searching for one. With only one word to find, a straightforward approach to find a single word is to iterate through each cell of the board, and whenever we come across the very first letter in the word, we are gonna perform a DFS, a depth first search, to search through the 4 angles, the 4 adjacent cells, if we can find the corresponding word again, which corresponds to the second letter in the string in the word, right? Fine, we have found S, right? And then because S corresponds to the very first letter, then we try to perform a DFS search to R, to T, and if probably it has a left, or consider this A now. A have a adjacent cell toward the up and toward the bottom, right? So and toward the left and toward the right, toward the left and toward the right. So similarly, we are gonna try to search through all 4 adjacent cells of S. So searching through it, we can't find it here because this is R, but we can find the next letter in the word. We can find it here. This is T, and because we find it, we are gonna perform a DFS again to consider every other the adjacent cell if we can find the remaining words. for starting from node T, right? I mean this cell T. So doing the same thing again and again, we come across A and we come across R. So but we see that there is a need to backtrack here. Why? Because there is no way we can find E. We have got to a dead point, or how would I call it? So there's no way we can find E, because if consider every possible adjacent cells to R, it does not contain a E. So we have to find we have to backtrack back to A. So and then because of that, after backtracking back to A, we still cannot find any other R apart from this R here, right? So we backtrack again from A to T. So and now what we need right now is A. So because we can find another A apart from this that has not been visited, then we try to search for it again, and luckily we found A here. So in this problem we will be exploring some ideas on backtracking, even though we are still gonna go into full details on backtracking very soon in the future in the subsequent coming videos, but we just are gonna explain the give some hints concerning how to backtrack recursively. The above approach that I just explained actually work well for one word, at least quite efficient, but trying to do that for until we find every word in the array of words could be very expensive. Imagine doing this for S, and let's say that the array also contains tam, doing it again for M and contain var, doing it again for R could be very expensive, because it's not only about trying to figure out the possible word, it's also about backtracking every single time, so it can be expensive. Now let's say it's not just one word, but it is two words, and the words are bytes and byte. Let's say the word contain byte as well as bytes. So once we find bytes by traversing the array like this, byte, we are just like to efficiently continue to find bytes by just extending the search by just one word, by just one cell, right? Rather, this is where trie data structure comes in, as it is very good and great in managing prefix. So if you can look, byte and byte have the same prefix up to byte, right? So and this way, if we could utilize the efficiency of tries, we can be able to just get these two words in a less redundant manner. I mean, we can easily get bytes and just get the second one bytes in a single in just a single step. Now let's begin creating the trie by inserting each word from the words array that is provided for us. We can see that by creating a trie and populating it with the words bytes, rat, rain, trait, and train, we are going to effectively and efficiently create this particular structure. So if you look at the previous video we've done on design a tree, insert and search with wildcards, the subsequent video we have done on tree, you will know how to create tree out of this list of strings. Now you will notice that we use the attribute word to represent the end of the string here. So whereas in our previous videos we have been using a word which is a boolean, so whether that is the end of the word or not. So instead of having word here, it will just be a word, and it will be a true or false variable, right? Like, but you can see right here that we're actually using the word to be represented here. Look here, we have bytes, and the word that is set, the word attribute is set to bytes, which is the word that is formed at this point. So similarly here, it is set to bytes. Right here it's just byte, but here is byte. Similarly here we have rat, we have rain, because that is the word that is particularly formed and end at this particular node. So you will understand why we are doing this later. Now let's use this trie to search for words over the board. We do this by seeing if any part in this trie corresponds to any part in the board. So what I'm trying to say is that look at this part, for instance, byte. This is a part in the trie. This is another part. You see, a rat or rain or train or trait, they're all parts in the board. So we're just gonna look if it corresponds to a part also in the board. This is a part in the trie, sorry. So we just want to check if it corresponds to a part in the board, just like you can see here. So by using the part in the tree, we can check if it corresponds to a part in the board, and then if we get to a part in the board in such that the that it represents the end of the word, then we can know that okay, we've gotten to the end. You understand? Well, if you don't understand, you're gonna understand in the next few moments. Similarly to how we use backtracking to find a word when searching through the board. So for a single word, in our first explanation, we try to check okay, how can we actually search for a single word in the board, and we did that using backtracking, right? So similarly to that, we are gonna see how to use backtracking to actually search through multiple words with the aid of the tree structure. The first step is to traverse and go through this board cell by cell until we get to a cell that actually match any one of these root nodes children. So and as we go through the cell, as we traverse through the board, we see that the very first cell at row 0 and column 0 actually contain the character B, which matches one of the root node child, which is this node B, right? So and now because we have found one that matches a cell that have a character that matches the root node, what we want to do then is that we are going to perform a DFS right from this particular node. DFS is just like a recursion, so we are going to perform recursion right from this particular cell. We are gonna try to check every adjacent cell, every possible adjacent cell from this cell. So and the possible adjacent cells are R and Y. Adjacent cells are cells that are vertically neighbor to this particular cell, or horizontally neighbor to this particular cell. So and this is just the two cells that are vertically and horizontally neighbor to it. So and then what we want to do is that we'll perform a DFS on each of these to try to check if we can find a word in the board that actually matches the word that extends from this particular node. So now when we perform the DFS to the adjacent cell, we eventually try to check at this particular horizontal neighbor of B. Fine. So we try to look at this horizontal neighbor of B, which is Y, and then we see that it corresponds to the child of the node B, right? So what we want to do again is that we are going to perform another DFS right from this point, from this cell, to go and check its possible adjacent cells that could match any branch that is extending from Y, right? So when we perform a recursive call to this particular node, to this particular cell here, right now, we see that it matches the child of a child of Y. Actually, Y has only one child. I mean, the node Y in the trie has only one child, T. So now that it matches it, so what we want to do again is that we want to perform a DFS starting from this T again. So that's how we just do it on and on. And when we perform a DFS starting from this T, we come across we are gonna try to check every adjacent cell to T, which include adjacent cells are cells that are horizontal or vertical to it. So and when we try to go through and perform DFS on each adjacent, we see that this particular one matches a child of the node C again, and because of that we are gonna perform a DFS on this particular node again to go. What we are trying to do is just to traverse the board and to try to check if it actually corresponds to any part or any branch in the trie. So we will just keep on traversing like that, and when we get to E now, so we say that E actually is the end of the word. Why? Because it has word attributes not set to none but set to byte. So definitely it means that we have found by traversing the board, we have found the word byte, so we can then add the word byte to our output array. The problem is to the problem wants us to try to figure out how many words in the array can be formed by traversing the board, right? So we have an array of words that is given to us. So this array of words could contain any number of words. So we just want to check that in this board how many words can be formed. So all those words we want to keep in. If we find a word that can be formed in the board, we are going to add it to the output array. So now that we found byte, why? Because fine, we are able to traverse the board from B to Y to T, trying to check through the node if it correlates, and now we got to E. But because E has the word attribute set to byte, it means that it is the end of the word. That node E is the end of a word, and the word that ends there is byte. So we're gonna add that to our res, which is our output array. So we're not gonna stop there. We just keep on traversing. We're gonna do a DFS again on E to go and look at all adjacent cell. So keeping track of the one we visited. We don't want to go back to the one we visited. Don't forget the problem said we should not revisit. We should not use the same node twice for a single word. You understand? So because of that, we are just gonna, from E, you see that we are E, so we're gonna try to check every adjacent cell again, and so far the valid adjacent cell that we can check is S. Why? Because we visited Y, we visited C, so just S that is remaining. So this is it here, X, right? And you see that this S also forms a word because it has the word attribute set to bytes. So here is bytes now, so we are gonna add bytes to the this one is the word that is formed at node E, but this is the word that is formed at node S, which is bytes here. So we're gonna add that into the array. So we see that by traversing, starting from the very first cell, traversing through adjacent cell to try to check anyone that matches that particular that matches any branch that extend from that particular character B. You understand? We look into B, which happens to be the very first cell in the board, and this B also happens to be one of the root node. It matches with one of the root node, which is this node B, right? So because of that, we perform a DFS to try to check if we can find any word that branches from B, if we can find it in the board. So, and then by doing the search, we found Y, which is actually an immediate child of B, so that branches from B, right? So because of that, we tap into Y also, and we try to perform a DFS, and then we found T, and then we find E, then we find S, and then that way we found two words from that that is formed from that part. Right now, what we're gonna do again is we'll backtrack. You understand? Because at this point S here, you will see that there is no way we can perform a DFS any longer. Is there? No. Why? Because there is no valid adjacent cell to S. Every adjacent cell have actually been visited in this part. So because of that, what we wanna do is to backtrack. So what we're gonna do is to backtrack back to B, and then doing that, we just want to start again with the very next cell. Right, we've tried to check every possible path that we can find from B that matches a branch that matches this, and we found two words, right? So what we want to do is just go on to consider the very next cell, which is Y now, and try to check if it corresponds to any root, or let me say if it corresponds to any children of the root node. So if we do, then we start to do try to check it out again. But if you can see that Y actually does not correspond to any child of the root node. So what we do is that we move to S, we move to R, we move to T. You understand? Fine. R do. So we just keep on doing the same thing, because R corresponds to a particular child of the root node. Because of that, we are gonna perform a DFS on R. So that way we'll be able to traverse to A, to I, to N, and then that's how we keep on solving this problem. Look at now. So but now one thing we need to consider is how do we keep track of visited cells, because as you can see here, let's say that let's say this, let's say that, okay, after traversing through the each cell in the board, right? Don't forget, we said we're going to traverse 3 cells. After finding BYTE and BYTES, then want to move on to Y to try to check if it corresponds to anything on the root, any child of the root. So because it does not, we are going to move on to S. Because S2 does not correspond, we only have node B, node R, node C. So S does not correspond, so move on to node R. Fine. So let's say that we move on to node now, and we did the same thing that we do to bytes. We try to traverse and we got to rain, RAIN, and we added it into our output res. Now let's say that we are now at C. You will see that right from this node T, fine, T corresponds to a particular child of the root node, right? So because of that, we are going to perform a DFS back to R, so that it could be TR. R also corresponds, then A also corresponds, then I also corresponds. I mean, if you look at this branch here, the part here, you see that I also corresponds. Now we could do a mistake whereby we will revisit T. Don't forget that T is already chosen in forming this particular this particular word. We already take TRAI. Now it will be a mistake and an error if we go back to T, because we are revisiting the node that we already used. So P was actually previously visited here. So to avoid that, we need to find a way and figure out a way whereby T will be each time we visit a node, that node will be set to visited. So it's either we use a hash map or a hash set, so that the visited node will be added to the hash set, and we can try to check for each node in the hash set if that node is not visited. So in O1 time, I mean in constant time, you can just try to check if, let's say we go to high now and then want to return back to T, we can just try to check if node T is not in hash set. If it is in the hash set, then we know it is visited. But another way we can do it is to just hash it, like by changing the value to hash. Imagine now something like this. Each time we visit the node, we change the number to hash. So then when we come here, we change it to hash, So by the time we got here, you will know that fine, we've gotten to the node I, and because node I corresponds to this particular this cell I, or cell containing the character I, and because this particular cell because this particular cell I here corresponds to this node I, so we just wanna keep on traversing through the board. So if we should return even I, because this I corresponds to a particular node in the path, right from here, TRAI. So we want to perform a DFS on the adjacent cells. Now because we have set this one to hash after we because it's a visited node, so each node that we visit, we try to set it to hash, and because of that, when it's come to this particular node up here, it will see that it is hash. And definitely, since hash does not represent any child of the node I in the trie node, is not gonna work out. So it's just gonna consider every other part, and that way it's not gonna visit it again. I hope you understand. So what I'm trying to say in essence is that, imagine if we not convert it to hash, it will be T, and because T is one of the child, we could mistake it for a valid cell that has not been visited. And then imagine now we now added TRAIT into the output array. So that way now there's a problem. Why? Because there's no way we want to get TRAI. There's only a single T inside this board, so, and therefore the board cannot form the word TRAIT. So but the mistake, what caused the mistake, is because we actually revisited an already visited node, and to avoid that, we are gonna set it to hash, so that when you come and check the child nodes, it's not gonna find hash there, right? Because hash is never a node in the trie. So, and because of that, it's not gonna work for this. Then it's gonna come back and perform a DFS on this other adjacent cell, and it's gonna get train. So, and eventually train will be added to the output array. So to summarize, how we'll be solving this problem, the first thing is actually simple. The first thing is that we try to check if the current node represents the end of the word. Oh, sorry about that. Actually, I want to summarize what we are going to be doing at each DFS call, right? Don't forget that imagine when we are just starting up here, here we try to check, we are gonna navigate through each and every cell in the board. So if the cell actually corresponds to a child of the root node, definitely we want to perform a DFS if we can find, to check if we can find any word on the board that actually correspond with that branch. Imagine now, when we traverse through the board cell by cell, we found the node B, we found a cell with value B, right? And this value B corresponds to the node B, which is a direct child of the root. Definitely it represents the start of a word. Now what we want to do is I want to perform a DFS on starting from this particular cell to check if the board could contain any word that could branch from this node B. So, and then at each DFS call, what we want to do is this: we want to check if the current node represents the end of a word. If it does, we want to add that word to the output, and that's what happens right here. So right here, whereby as we are traversing and trying to check if each of this if the value of each of this cell is in the is a child of the current node. So just like in this case, look at in this case now we are currently at T, and when we perform a DFS, we'll try to look at this adjacent cell to T, and because we found that it is a direct child of the node T, because of that definitely it is a valid, like it is actually direct child. So and because of that we will first of all check if it has the word attribute set to a word. If it is, we want to add it to the rest. Why? Because we definitely have taken through a path, and that path has led us to a word, right? And then we want to add that word to the rest. So that's what this place is trying to tell us. So at each node of the current node, at each of the current node, as we navigate using the DFS, we want to check if it has the end attribute, if it has the word attribute set to a word. If it is not set to none, because it will be set to none by default. So but if it is set to a word, that is, it represents the end of the word, then we add that word to the output. So then what one adds is that I want to mark the current cell as visited by setting the cell to hash in order to avoid revisiting an already visited cell. Then what one adds is that I want to recursively explore all adjacent cell that corresponds with a child of the current trie node. What this place is trying to say is that after, just like here now, after we found the word here, we don't stop there. We just try to recursively perform a DFS again on each of the valid node, that is the ones that have not been visited. So to try to check for any other word that can be formed, you understand, in the board. So and then what we now do at last is that we backtrack by reverting the cell back to the original character. So it means this one trying to say that after we find the word, we are going to be needing to set this particular character back to the original ones. So I mean this one now back to I, and then this one now back to A, and then because after we've gotten to the very last node and whereby we cannot perform any more recursion, we want to backtrack, because after backtracking we will need to move on to the next cell. Don't forget, we'll be actually passing through and going through each and every cell to try to check if they corresponds to any child of the root node, right? So we want to backtrack it so that this cell won't be so that when we are trying to perform DFS on any other cell, it won't be hash, it won't just be hash. So and that's how we solve this problem. Well, it might look a little bit complex in logic, but you will understand this fully in the code implementation. Alright, let's go into the code implementation for the find all words on a board. So we are gonna be defining our class, our tree node class. So you know, with the tree structure, including the tree node, each node in the trie, the tree node class that represents each node in the trie, and the trie structure, you know, which is represented by a trie with this insert method and the search method. I'm gonna just drop it right here like this. You can go to my previous video for a more better understanding of how to define a trie, how to create or design a trie data structure. So I did a video on that, and if I should be repeating it here, it's gonna take too much time. So but this is just a try for the insertion and search. Don't forget that according to the logic, we are gonna define a try. In fact, we are gonna insert every word in the array into the try. So what we just want to do is that after creating that try and populating it with the words in the array, we want to traverse through to go through the board cell by cell and try to check if any of them corresponds to any child of the root node. If we do, then we want to perform a recursive call. You understand? We want to perform a DFS, like we want to recursively call each and every adjacent cell of that particular cell to try to see if we can form a word in the board that actually corresponds to a part, a branch, a word in the try. So it's just like we are trying to navigate the board and we are trying to use the try as a reference that, okay, since the try contains every possible word, now let's see how much word we can form by traversing and iterating through the board. So whereby we'll be using the try as a point of reference. So this is the data structure now for the try. Now we are going to be populating it. So the first thing is that we define an instance of the try. So this is the try. We create an instance here, and then this is the array of words that is given to us in the problem statement. If you look at the problem statement, you see that we are given an array of words that we want to try to check if they can be formed in the board. So, and whereby this is the board as well, right? So now what we want to do is that we want to iterate through each word in words in the array of words, and we want to insert it into the try. So try IEE dot insert. So insert each possible word that could be formed in the board. So we are trying to insert it into the try now, and that's what we just did. So now that we have our try, let's define the function that will help us to find all the words on the board. So this function is going to be taken in the try, right? So why? Because we need to be comparing the board as we are doing the DFS call at each node. We have to comparing it with the nodes in the at each cell, as we are trying to compare and do a DFS on each cell in the board. We are going to be comparing it with the node if they actually align, so and if they actually form any real word in the node. So this try is actually going to be a try node, right? So we're all going to be passing our board BOARD, which is actually a list of string, right? So right down here also, let me just pass in the print function to print the. So you see that we pass in the try that we just created here. So and we just populated with the words, and also passing the board, this particular board here. So and the return will also be a list of string, right, which actually corresponds to possible string that can be formed in the board. Now we'll be collecting the length of the board, the rows, number of rows in the board as length of board. So because when we have is a 2D array, so when we perform the length, it's gonna tell us the length of the rows. So whereas you can collect the column as length of board of 0. So we just take a single row and check the length of that single row, so that represents the column. So and after that, let's define initiate our row and column to be 0, because we are going to be traversing through the board cell by cell. So and you can do that by using rows and column. You know, row 0 0 corresponds to the first row, first column. 0 1 corresponds to first row, second column. 0 2 and so on like that. So that will be traversing through the board. So also let's define this dirs, which will be used to search for adjacent cell. So it's going to be set to 0, 1, which means that the row should be the same for a particular cell. The row should be the same, but the column should be a +1. So that way we can try to check for the cell that is to its right. I mean the cell to the right, the same row, but the column is now +1. So we're also passing 1,0 also passing -1,0. So all of these are representing the coordinate adjacent cell, 0, -1. And then we are going to iterate through each cell in the board now. For R in range of M, don't forget M represents the number of cells. So for C in range of N, so and then what I want to do is I want to check if board of R of C. So I want to check if the value at this particular cell, if it is a child of the root node. Now how do we get the root node? So don't forget we've passed in the trie node to it and we have populated it. So then we just define the root node to be trie dot root. So don't forget that trie is actually an instance of the trie class, and then we already defined the root node here, self.root, so we can use that root node now. And don't forget we have inserted every word in the words array into the array, so we can access them through the roots. So now that we have defined the node here as the root node, we just try to check if this is in node.children. If it is in node.children, then we want to perform a DFS call to it. Don't forget in the logic we're going to be performing a DFS call to its adjacent cells, which is represented by this coordinate dirs. So but we are going to be dividing that in a separate function. We pass in R, we pass in C, which actually represent the coordinate of the current row and column. Also we'll be passing in the node.children, the node that we are currently at. Don't forget that before we could call DFS, we need to ensure that that particular cell have a value that corresponds to any one of the child in the root node, right? So we want to pass in that particular child, so BOARD of R of C. So also we'll be passing in the board for reference purpose, and passing in DRS for reference purpose. So now let's define the DFS function, right? So let's define this function. We'll also be collecting all the things we passed in. So C, which is an integer, so the node, which is a trie node, so and then we're passing in a board, which is also a list of strings, right? We're also passing dirs, so which is actually the directories for where we can find the adjacent cells, so which is also a list of string integers, right? And then the return of this one, well, let's just still leave the return. So now first of all we just want to check if this particular node have the word attributes, meaning that if the word attribute is not set to none, and in cases like that we want to append it into our results. Don't forget that if the word attribute is not set to word, definitely it means that that current node that we are actually represent the end of the word. That is, we have been able to traverse and to go through the board until we get to a particular cell that actually represent the end of the word, and because of that we have to add it to a node. So let's to a cell, to the output cell. So let's define that as this. So right, let's define it as res as our output. So don't forget, because we define it outside the function, we will actually need to set it to global here. So we have global res so that we can use it and modify it here. So res dot append that particular word, and because of that we need to set our word back to none, so that in the process of traversing again through in the process of traversing for the rest of the word whenever we come across this node, so we won't input it into the result again, so we won't be having multiple word in the result. So we have to set that word to none, that word attribute, not even word, it's supposed to be node.word, so we set node.word to none, right? So that's how to solve this problem. We set node.word to none. So now what we want to do is that we want to set, let's collect the board of R of C, right? Meaning that the value there, we collected it temporarily, and what we want to do is that I want to set that particular value to hash, so that we will know that it has been visited. So don't forget, that's what we want to do in the logic, so that we won't go back to the same word, we won't use the same letter twice in a single word. So we are going to set it to hash now. So later in the process of backtracking, we are going to set it back to temp. That's why I collected it as a variable template, so we can set it back later. So for dir in dirs, don't forget, what we are essentially doing is that we want to go into each adjacent cell to try to check if they correlate, if they actually correlate to a child of the current node. If they do, then it's possible they are going to, that part is going to lead us to the next word that we are finding. So if board of R, now one thing you need to notice that we are going to be creating a new row and a new column. Don't forget that the adjacent cell won't be at the same row and at the same column, right? So we have to they are going to be, we are going to take this dir of 0, we are going to add it to our existing row, and similarly our column also will be dir of 1 plus the existing, let me just say plus the existing column. Why? Because when we say adjacent, it is to the left, it's either adjacent to the horizontally, to the left, to the right, to the top, or to the bottom. So we are gonna be for each possible way. That's why I have the dirs method. That's why we define this method here as 0, 1, 1,0. So the first elements in each of the lists represent the row, while the second represent the column. So at any way, you see that we don't have anything like a 0, 0. When we have 0, 0, it means that same cell, so we don't have it. So we are just trying to look at one added, one removed. So that's what we are doing. So as to look at the adjacent cells. So now we are now gonna perform a DFS. So okay, now that we have this, now what we wanna do is that we want to check if it's within bound. So you need to understand that not all of these adjacent cells are gonna exist. For example, now in our in this thing that we check, let me go back to it here. Okay, consider this particular first cell here. You see that it does not have any adjacent cell to the left or to the top. The only two adjacent cells we have is R and Y, right? So similarly, consider this N here. You see that it does not have any adjacent cell to the right or to the bottom. It only have to the left and to the top. So because of that, we need to be able to cache out to manage adjacent cell that does not exist. So we need to make sure that it is within the bound of the maximum row and the minimum row. So we are going to understand what I'm trying to talk about here, whereby we're passing in the row, this newly created row, this newly created column, and I'm going to be passing in the board as well. So if it is within bound, that is, it's possible, it is not going to give us index out of index error. If it's not going to be a negative index, or maybe a index that is actually greater than the number of rows. So that's what we are trying to cache there. So we'll be defining a function is within bound. So if it is within bound and board of row, so if it is not within bound, if we perform index like this on the board, it's gonna return error, because row could be larger than every than the supposed rows or supposed column. Don't forget that we'll be adding the dir of 0 there, so it's gonna be changing the row and the column. So if it's within bound and this is in node.children, the current node dot children, then what we wanna do is just to perform the same DFS call on it again. DFS of now it will be row, so that we can check the adjacent rows. So it will be row and column, which represent this new row and column, and then we just keep doing that. So now, if in the process of backtracking, what we now do is that we want to change our board of R of C back to temp. So don't forget we've collected it here. So you see how we backtrack. So that way now, that's actually after each of them have been called and DFS have been called on each of them, and the function have finished evaluating. Is gonna, for each of them, is gonna reset their value back from hash. So now let's define the is within bound function. Is within bound function is gonna take in the row, the column, and the board. Right. So and then the return is a boolean, right? So fine, what we want to return is gonna be a simple function. You just want to check if R is less than equals to if 0 is less than equals to R, which is less than len of board board of 0. And what this does actually is that it tries to check if the row of the adjacent cells that we calculated here as ROW and COW that we want to check, that we pass into the is within bound right here. We want to check if this row actually makes sense to the board. If it's between 0, if the row is between 0 and the length of board, it must not include the length, because in Python when we are indexing, it is 0 based, it is 0 indexed. So it must be less than length of board, so meaning that it must not be more than length of board minus 1, right? So similarly, we need to do the same for the column too. So column must be between 0 and length of board of 0. Sorry, this one is just supposed to be length of board. So length of board represents the number of rows, while length of board of 0 represents the other one. So this is supposed to be C. So it's gonna return whether true or false. So if it returns false, definitely the adjacent index does not exist, and we don't need to even move on. We just need to move on to the next possible adjacent index. So, and that's how to solve this problem. So let's run it and see how it goes. I know it might look a little bit intimidating, so probably because of the nature of the problem, so it can be complex. So but I just want you to go through it step by step and follow the logic first. Okay, when I run the code, it gives me none, and why is because in the process of calling this function, the find all words on the board, this function find all words, we don't return anything. So, and what we need to do is that hopefully by the time we have to set this to global rest, right? So, and by the time we finish iterating through each board, which we did there, we try to iterate through each board and call DFS on anyone that actually corresponds to the a child of the root node. So hopefully we are gonna be having all our rest populated that each call to DFS with every word that can be formed by actually going through the board, right? So, and because of that, we are gonna return rest simply after iterating through each board. So let's run it iterating through each cell in the board. So now thank God we have this passed, but what is passed is actually train, which is not what we want. So I guess there's an issue somewhere. Let's see. it's actually passing train. So sorry, we have to this place I'm trying to append word, and it's not supposed to be word, it's supposed to be node.word. So right, why? Because we are trying to append the particular words that end at that node. So now we have bytes, rain, train. So you see, we solved this problem and it actually worked out. So but I'm very sorry, it could look complex. I totally understand, and I totally really understand, but you can go through it again and again for more better understanding. Thank you.